No, they're orthogonal. I changed the problem because it should be any integer, right?
Yeah, but then like
They're orthogonal. They're orthogonal no matter what.
Okay.
Yeah.
But then would you have to show it a different way because then 1 minus m squared over n squared would be equal to 0?
Yeah. Then you would, I guess, show it different. Oh, yeah, that's a good point. So if m was equal to n, then you would have to do something different. Good point. Okay, so yeah, that's a really good point. Yeah, so I need to think about that.
You could just solve the integral with like a U substitution.
Yeah, so I guess you would just solve it for a U substitution. Or let's see, you just solve it by, yeah, you just get 2 on the other side, right? Or let's see. So I actually would need to work that out. Should we do that right now?
I thought they were equal at first. So.
Yeah. So, so you said if m is equal, so if you have cosine x and sine of x. Okay, so we want this to be 0, or 0 to 2 pi. Okay.
That's equal to 1/2 sine of.
Oh, so you're saying this is, what did you say?
I think that's equal to 1/2 sine of 2x.
This is my half angle formulas, you're saying?
I think so.
So shouldn't there be like a sine square? Let's see, sine. So this is, let's see, sine of this one. So this is sine of alpha, sine of beta, plus, or sine of alpha cosine beta, sine of beta cosine of alpha. Okay, and so this one is, so you have sine of 2 alpha. This is 2 sine of alpha cosine of beta, like this. Or cosine of alpha, like this. So you'd use this formula, right? And then integrate like that. So that's a good way of doing it, yeah. So then you can apply this. And then this one should be 0, because this is the same thing as the integral from minus pi to pi of 1/2 sine 2x dx, and then this thing is odd. Right? So that's another way of doing that. All right. So this is one way. That's another way. Okay. So I'm going to erase this, and I'm going to start with these boundary value problems. So the objective is to answer the question. Understand boundary value ODEs. Okay, and so I picked some problems from the book to do. Okay, so let me chop the board up. Yeah. Okay, so let's do the following problem. So this was so this is problem. So what was this? 3 point. Do you guys remember the section? One of these. 3.9. So section 3.9. Okay, so these problems come from section 3.9 of the book, and so I did some of the odd numbered ones. So one way to do this is to look at the odd numbered answers in the back. And so I think I found one where the answer in the back was not the same as the thing that I got. So, but the other two were the exact same. And then I checked it. So, so this is problem 15. Okay, and it says to solve the following thing: y prime prime plus lambda y is equal to 0. Y prime 0 is equal to 0, and y of pi is equal to 0. Okay, so we're going to solve this. So what we're going to do is we're going to solve for possible, so solve for possible lambda and find the associated eigenfunction. Okay, and so to do this, the procedure is the same for all of these, is that we're going to write down a general solution, and then we're going to plug in the boundary conditions, and then try and figure out what happens to the lambdas and what happens to the coefficients. Okay, so we'll write down a general solution. Okay, and to write down the general solution, right, we use that, so we have m squared, so the characteristic equation. So m squared plus lambda is equal to 0. Okay, so I'm going to write, so we're looking for solutions of the form e to the mt, or e to the mx, depending, I didn't really specify, but I'm going to use t as an independent variable. Okay, and so this tells us that m is equal to plus or minus the square root of negative lambda. Okay, and so I'm just going to use m1 all the time. So the general solution, so let m1 be one of these roots. Let's say the square root of minus lambda. Okay, and so the general solution has the form this. It looks like c1 e to the m1t plus c2 e to the minus m1t. So that's the general solution. Okay, and so now we plug in the boundary conditions. Okay, and the boundary conditions here, so we need to compute what y prime is. Y prime of t, so this is c1 m1 e to the mt, m1t, plus c2, let's do minus c2 m1 e to the minus m1t. Okay, so that's what y prime is. And so let's just copy down what the boundary conditions are here. So the boundary conditions, so these are these two things here. So y prime of 0 is 0. And y of pi is 0. So these give, now I just plug them in. So y prime of 0, that is c1 m1 minus c2 m1 is equal to 0. So that's the top equation here coming from this one. And the other one is we plug in pi. So then we have c1 e to the m1 pi plus c2 e to the m2 pi is equal to 0. Okay, so those are the two equations that we have. And these should give all our conditions, let's do, this is still true, but I'm going to do minus m1 here. Okay? All right. All right, so now, okay, so there's one case that we have here. So let's label these things. This is equation 1 and this is equation 2. So by equation 1, right, we have c1 minus c2, m1 is equal to 0. So this implies that c1 minus c2 is equal to 0 or m1 is equal to 0. Okay, so if m1 is equal to 0, this implies lambda is equal to 0, right, because of this relationship here. Okay, and so this tells us that y of t is actually a different solution. So this is for, by the way, this is for m. So for lambda not equal to 0 here, right? So this tells us that this has the form a plus bt. Okay, so the boundary conditions on this one tell us that y prime of 0, right? So this is equal to b evaluated at 0. This is y prime of 0. This is just b, and this is equal to 0, right? And y of pi then becomes a, right? And this is equal to 0 as well, right? Okay, so this tells us that this implies that y of t is the 0 solution. So we get the trivial solution. So it's a trivial solution when this happens. Okay, so if we're in this case, we get the trivial solution. So let's focus on this case. Okay, so if C1 is equal to C2, then what do we happen? Then we can plug this into the second equation. Then 2 gives the following, that C1, so 0 is equal to C1 e to the m1 pi plus C1 e to the minus m1 pi. Okay, and so this tells us that so 0 is equal to C1 e to the m1 pi plus e to the minus m1 pi. So we get, again, two things. So C1 is equal to 0, or e to the m1 pi plus e to the minus m1 pi is equal to 0. So if this one's equal to 0, this implies C2 is equal to 0, and we get the trivial solution again. Trivial solution. Okay? So now we're going to suppose that the other equation is true. So if e to the m1 pi plus e to the minus m1 pi is equal to 0. Okay? Okay, so now this tells us that e to the m1 pi is equal to negative e to the minus m1 pi. Right? And then we can multiply both sides of that equation by e to the m1. Okay, so this tells us that e to the 2 m1 pi. So I just here you just add the exponents of things with like bases is equal to minus 1. You guys agree with that? Okay, so this thing here is equal to e to the I pi, right? Plus 2 pi n for n an integer. Okay, so this is 2 pi I n. Okay, so this tells us that 2m1 pi is equal to I pi plus 2 pi n I. All right, and now we can get rid of the pi's. The m1 is equal to, well, so the pi's go away here. And then we have, so this is 2n plus 1 I divided by 2. All right, so that's what I got for n an integer. All right. So, so what does that give us? So let's look at this thing. So now we will write mn is equal to 2n plus 1 divided by 2i, right, for n an integer. Right, and then this tells us that lambda, so then mn is the square root of minus lambda n, right? And so this tells us that mn squared is minus lambda n, okay? But mn squared, on the other hand, is what we just computed, right? So mn squared is equal to 2n plus 1 over 2 squared, and then we have a minus here. So this tells us that lambda n is minus 2n, well, we could say n plus a half squared. Okay, so this is what, these are our eigenvalues. Okay, and now we can plug this into our solution, right? So let's plug this in. So our solution. So we have y of t looks like, okay, so we know that c1 and c2 are the same. c1, and then we have e to the m1t plus e to the minus m1t. And so this is c1, and then we have e to the I, well, mnt, or sorry, not I, mn, but let's do e to the I, and then I'll just have to write it out, I guess. 2n plus 1 over 2t plus e to the minus I, 2n plus 1 over 2t. Right? And so do you guys recognize that one? So this is 2. So this is c1, and then we have 2 cosine of 2n plus 1 over 2t. Right? Like this. Okay, so this tells us what our yn should be, because it's really up to a constant, right? So we let yn be this function, cosine, right? Okay, so this is this, and so this is our thing here. So we have our eigenvalues, and then we have our eigenfunctions like this. All right. Let's see if I got the same thing as when I did before. 2n plus 1 over 2. Yep. Okay, so that's what I got. All right. And so the book actually has something different, and so they say that. So I checked this again. So you guys should check this. So the book did cosine of. So they said nt was equal to yn of t. So maybe this is from an older edition or something. All right. And then what they have for the eigenvalues? And lambda n was n squared. So the back of the book. So the back of the book has the odd numbered exercises, okay? But we can check this again, right? So so like here, if we use this one here, so notice that so yn so yeah, yn of pi. So this was one of our conditions, right? So from the original thing, we wanted the initial condition at yn of pi, right? So so this thing here is cosine. So for the book version, right? So this is cosine of n pi. So this is equal to negative 1 to the n, right? And so this is not equal to 0 always. If you do it like that. All right. Anyway, I just wanted to point that out. Why? So it's imaginary.
Yeah, so then you say mn squared is negative that, but then isn't lambda equal to...
Oh, it should be, let's see. This is negative, right? So mn squared is this, and this should be negative. You're right. So yeah, this should be negative. This is this. Yeah, you're completely correct. Yeah. Thank you. Yeah. So here I forgot a sign. Yeah. Thank you. All right. Any questions on this one? This freaked me out when I saw it in the back of the book. I was like, what's going on?
So for the quiz on Friday, or on Wednesday?
Yeah.
What we have to do?
So yeah, for the quiz on Wednesday, I'm going to give you one, something like that, something like that. So I'm going to do some harder ones now, though. But yeah, it'll be something like this, yeah. So it'll be one of the ones that I gave you from the homework. Yeah. Okay, so let me do a harder one, okay? And then I've got one more harder one, and we'll see if we get to that. So let's do another one. So this is So number 19 from section 3.9. Okay, so here's another one, right? So here it will have x squared y prime prime plus xy prime plus lambda y is equal to 0, right? And then we have y1 is equal to 0 and y e to the pi is equal to 0. Okay? So solve this boundary value problem. Okay, so this one's a little trickier because this has non-constant coefficients. Okay, so there's a trick. So here's the solution. So again, we find the general solution, and then we plug in the boundary values. So we need to find the general solution of this thing. So it's a little trickier. Because of the non-constant coefficients. Okay, and so earlier in the book, they give some methods for solving these things. So and it turns out when you have something like a square, so this matches the power here, there's a trick you can do. So here's a trick. So let me do the general solution. So the general solution so we'll do y of x. So we try y of x is equal to x to the r for some, let's say, r, a real number. Okay? All right? So we'll try this, or some r. Let's just say some r. We don't care what it is. All right? And so what we're going to do is we put this into our equation. And so this works. Okay, so let me just tell you something. So you can always try this, right? So the thing that you can do. But one thing you can try it's kind of productive to do is to do this. So you've seen power series solutions of differential equations. That comes up quite frequently. And so you get special functions this way. But you can do this times a power series solution where this is not necessarily an integer. Okay? So that's kind of a useful thing to do sometimes. And we might see that later. Because we'll take some equations, we'll separate some variables, and we'll get boundary value problems, and we'll have to actually deal with that. All right? All right, so let's plug this in. Okay, so we plug into our equation. And so the thing that we get here, since we're taking two derivatives, so we get, r minus 1, x to the r minus 2, plus x r x to the r minus 1, plus lambda x to the r is equal to 0. Okay, and so this tells us that we have this thing, and then we have this equation, r minus 1, plus r plus lambda is equal to 0. And so we have, so we were going to say that this thing's not 0, plus, and so this allows us to solve for the possible r. Okay, so let's solve for this. So this tells us that r squared minus r, right, plus r, plus lambda is equal to 0. So this term goes away. So r squared plus lambda is equal to 0. And this tells us that r is equal to plus or minus the square root of minus lambda. All right. Okay, and so so let's try this now. So let's say that okay, so let's say that m. So let's say m is equal to the square root of minus lambda. All right. So our solution looks like. So now have a general solution. And it looks like this. Y of x looks like c1 x to the m plus c2 x to the minus m. Okay? So this is what it should be. So we were looking for solutions like that. All right, and now we can write this out a little bit simpler. So this is going to be c1, and we can do e to the log of x to the, okay. So I'm going to write it like this, log. And so I really mean the logarithm of base e. Okay, so I'm going to write my log like that. Okay. So we have log x to the m. And so these two things will cancel, plus c2 e to the log x to the minus m. Okay, and so this is equal to c1 e to the m log x plus c2 e to the minus m log x. Okay, so this log is a natural log. All right. Okay, and this is what our solution looks like. And now maybe you can see where our, so this is what our general solution looks like. And now we can use our boundary conditions. So let's use our boundary conditions. All right. So we have y1 is equal to 0. So y1. And then we have y of e to the pi. So now you can see where this e to the pi, why they chose this e to the pi. It's kind of a, well, artificial thing. So then, so y1, log of 1 is 0. So that we have c1 plus c2 is equal to 0. This comes from the fact that log of 1 is equal to 0. Okay? So then we also have here, what do we have now? This one. So then we have c1 e to the m. So now we're plugging in log e to the pi, okay, plus c2 e to the minus m log e to the pi. And this is also equal to 0. Okay, and this gives us the following equation. c1 plus c2 is equal to 0. And then we have c1 e to the m pi plus c2 e to the minus m pi is equal to 0. All right, and this allows us to solve. Okay? So from this, these we get c1 is equal to minus c2. Okay, and then this implies that c1 e to the m pi minus c1 e to the minus m pi is equal to 0. All right, and then we can just bring this all to one side. Is equal to c1 e to the m. Well, okay. So so let me do it like this. So this tells us that c1 e to the m pi minus e to the minus m pi is equal to 0. So one of those two things is 0. So this tells us c1 is equal to 0, or this thing. Okay? So if c1 is equal to 0, we get the trivial solution. All right, because c2 needs to be 0. It forces c2 equal to 0. So if e to the m pi plus e to the minus m pi is equal to 0, what do we get? Okay, so now we go into this business again. So this tells us that e to the m pi is equal to, oh, sorry, this is a minus here. Right? This is a minus. Okay, so this is e to the minus m pi. Multiply both sides by m pi. So this goes e to the 2m pi is equal to 1. All All right, and then we do this thing again. So this is equal to, so since 1 is equal to e to the 2 pi n for n an integer, right, we keep going, right? So then this tells us that 2m pi is equal to 2 pi I n for n to z, which tells us that m is equal to I n for n to z. And now I should not forget my minus sign, right? So we will say, now we'll just do this mn is equal to in. Okay, and we have this thing minus lambda n, right? So this is equal to mn. Okay, and so now let's square both sides correctly, right? So this is minus lambda n is in squared. So implies that lambda n is equal to n squared. All right. So we have this one. Cool? All right, let me let you guys catch up for a second. Okay, so, all right, let me just keep going, right? Okay, so then let's plug it back into our solution. So let's put this back into our solution. So we had that yn of t was c1 e to the mnt, mn, oh sorry, not t, we're doing x's, right? Okay, e to the mn log x plus or minus? Plus, right? E to the minus mn log x, like so. Okay, and so this is equal to c1. And now we have e to the in log x plus e to the minus in log x. Okay, does that look familiar? So this thing is equal to c1 times 2 cosine of n log x. I think I have a sign off here, huh? So c1 plus c2, so this should be a minus sign actually. So do you guys agree here? So this should be actually be a minus sign. Because if the general solution, recall, so let me just do something real quick. So we had y of x was c1 e to the m log x plus c2 e to the minus m log x, right? And then we had c1 plus c2 is equal to 0. So this should be a minus sign here. Here. And then this becomes 2I sine n log x. Okay? And so, I guess I shouldn't call this yn, because I want to give yn a different name. Sorry about messing up your notes, right? Y is this, okay? And then we're going to just call y, since it's up to a constant, this is what we'll call yn this thing. We call this yn. Okay, so then, so the answer ends up being, that lambda n, So this was equal to n squared, right? And then yn of x was equal to sine of n log x. And so this is the natural log. Okay? So that's the way to get that one. It's sneaky, right? Because, you know, we have that. So I have one more. So maybe I can just give this one to you guys. So maybe I'll make a photocopy and just send it to you guys or something. Put it on the webpage, or right? So this is a degree 4 one. And so in the degree 4 one, you just have 4 equations. So for 4 equations, you'll have 4 boundary conditions. And then you need to play with those equations correctly, right? It's just a matter of doing the algebra correctly to end up getting the other conditions that spit out what the lambda n are, right? All right, so I'll send that to you guys so you guys can look at that one. Hopefully this was helpful. All right.